Hello, it's Keith here, and this is lesson 6 of my Z80 assembly programming tutorials. Today we're going to be looking at Z80 assembler directives and a few other tricks that we haven't covered so far. Now, up until now we've been looking at instructions on how those commands work within the Z80 processor, but the assembler does have a big part in what we can do, and how we use those commands also is going to make a fairly obvious huge difference. So today we're going to look at assembler directives, and these are commands that tell the assembler how to convert our code into bytes, and these have various functions and they can be very useful to us. We're going to look at a few of them today. The important thing with assembler directives is though that it does depend on your assembler. Now, the ones I'm looking at today usually exist in some form on other assemblers, but if you're not using VASM, the assembler I use, then you're going to need to take a look at the documentation for your assembler and find the equivalents and find what the limitations or the differences in syntax are for your assembler. Now, the other thing we're going to be looking at today is we're going to be looking at some simple tricks that I frequently use in my code, and I'm sure you will want to know. And so this is where we're starting to go from the concept of discussing the commands themselves to more advanced things you can do with those commands to build yourself shortcuts or tricks within your code that will do things that could be very useful to you. Now, of course, what I'm teaching you today is not even a tiny fraction of the possible tricks and things you could do with your commands, because there's practically an infinite amount. It's just some basic things that I think are worth looking at, and hopefully seeing these will start to encourage you to sort of look at ways of using the commands to build your own code structures and make programs that are capable of doing things that you need more efficiently. So if we just go over to this screen here, we'll have a look at this code here. So this is an example of some of the kind of compiler directives you might see in your code, and this is no way an exhaustive list, it's just a few examples. So the first one we've got here is a list command. Now, my programs all output the listing via the command line to a text file, and if you want to see it, you can look at that text file, and if you don't, you can just forget about it. On a modern fast processor, you know, that is just not worth worrying about. But on older machines or on the WinApe assembler, where the assembly goes to an output window, and outputting the listing with the list command does actually slow it down. So on that system, you might want to disable the listing or enable it using a compiler directive. Now, that of course is by no means the only directive. You also have the EQU directive, which I believe stands for equate, and this will define a value to a symbol. So in this case, we've defined the screen mode symbol as being the value 3. Other common ones which we'll look at today are the org statement. This is a compiler directive telling the assembler what the next byte of code's memory address will be, and this is used by the assembler to calculate things like labels, and also possibly to pad out the binary file if we're starting from a different memory address, although how that works will depend on your assembler, because some just change the labels, some don't like multiple org statements. It is very dependent on the assembler you're using. Now, another one here is defining a sequence of bytes. DB, we can say, which stands for defined bytes, and so we're defining a sequence of ASCII characters here, each of which will be 1 byte. Now, we've also got a label here, and arguably these are a bit like a directive as well. This is telling the code that there will be a symbol called program start, and the address, the value of that symbol will be the address of the next byte of code as this is compiled. Now, as I say, there's a huge range of compiler directives that exist, but it's going to depend on your assembler. So we're just going to see a few of the ones that I think are really essential for you to see today. And if you need to know more, you want to go to your assembler's documentation, which certainly should be somewhere, and find them. And also, when we're seeing things like macros today, we're looking at the VASM ones. But the things I'm teaching you today, it's almost certain there's going to be an equivalent on your assembler. You just need to look at the documentation to figure out how to do it. Okay, let's go over to our code and let's see it in action. So we'll be starting today on the ZX Spectrum. Now, some of the later examples won't work on that system, but the earlier ones will. So we'll try the Spectrum for starters. So here's our first piece of code here. And what we're doing here is we're going to be looking at labels and symbols. Now, we've seen these before, but I think it's worth just discussing them once again, being as we're going over all of this kind of thing. So labels are lines of code that we've defined with a piece of text at the start of the line with no indenting. As I said before, a command is indented, labels are not, so they're at the far left. And I always put a colon at the end, but VASM, I don't believe, requires you to do that. Now, these are basically a symbol, a label is effectively the same as a symbol. It's given a numeric value, and that numeric value is calculated by what the program counter will be at this line of code. And so this allows them to be used for jumps and also for reading and writing memory and things like that. But as I say, effectively, they're no different to a symbol. Now, a symbol is a text string that we give a numeric value, and again on VASM they need to be at the far left because, as I say, labels and symbols are effectively the same thing, but these are given an arbitrary value we specify. So I'm here by specifying that the I am a symbol equates to 1, 2, 3, 4 in hexadecimal. Now this symbol is a 16-bit value, but this one is 8-bit. Now this doesn't actually make a difference because these symbols are effectively text strings at this point, and we can use them in any way in our code, give or take, that we could use a numeric value. So for example here we've specified that HL is going to be loaded with the value I am a label. Now the next time here we're loading BC with I am a symbol, and then here we're loading the accumulator with the 8-bit one here, so this one here, and we'll see those in the results here. So here we've loaded HL with 6014. Now HL was loaded with I am a label, and so this has taken the value of the memory address of this line of the code here. As I say, this is a symbol, so it's not a program line of code, but it exists within the lines of our code, and that is effectively the byte of data here that would follow with the consecutive command after this label here. So that's what we've loaded there. Now what we've done then is we've loaded BC with 1, 2, 3, 4, and we've done that via this I am a symbol here, and of course we specified that value here, 1, 2, 3, 4, and then finally we loaded the accumulator with the 8-bit value here, hexadecimal 69, and you can see that's been loaded in here. Now all of this is being done by the assembler. When we actually compile this, the bytecode that is a result will actually contain the fact that the BC was loaded with 1, 2, 3, 4 and the A was loaded with hexadecimal 69. There will be no reference to I am a symbol or 8-bit in the compiled code. They'll have disappeared. So this is how they are different as a directive compared to a command, and a label also will in the same way be converted to the numeric memory address that I am a label contained at the point the code was compiled. And that is something that is worth mentioning. It's quite complicated, but when the assembler compiles the program, it typically scans the code twice, first time calculating the labels and the second time inserting them into the code. Now if you do very complex things with conditional compilation, which we'll look at later, and also some other things with regards to calculating symbols based on the values in other symbols, you can end up with code that's too complicated for the two passes of the assembler to actually calculate, and you might end up with bugs, and the only way you'll be able to find those bugs is by looking at the listing file and noticing that there's a mathematical error in the way that the labels and the symbols were calculated. Now that's very complicated. It's going to be way outside of what you're likely to need to worry about at this stage, but just keep it in the back of your mind, because one day you might be doing something incredibly clever. It should work, but it doesn't, and if you look at that listing file you might find that one of the labels has been miscalculated by the assembler because what you're doing is now too clever for the assembler, and usually the trick is to in some way pre-calculate the value in a symbol at the top of the code, so that when the code gets to the bit it's struggling with, it will have the value pre-calculated for it by that point, or to use fixed memory addresses rather than labels, things like that. As I say, it's just something to bear in mind at this point, that while the assembler does a great job of calculating these, it sometimes does make mistakes when maybe we're setting a label to be relative to another label, which is relative to a symbol that's defined at a later point in the code, things like that. So anyway, as I say, these are all string replacements, and it doesn't matter from the point of our code how we use them. So this 8-bit value here is only 8-bit at the point of compilation, so we can put this and load this 8-bit value into BC, and that will work just fine. Now effectively I think the best way to think about all this is that the assembler is basically doing a string match search and replace. So when we are doing this here, loading BC with the value 8-bit, the 8-bit value isn't really 8-bit, it's just the value hex 69, and so it's equivalent of us just writing in here and 69. That's basically what the assembler has done when it's come to this line of code. It's just swapped out the text for the value that we told it had, and of course that has worked just fine in loading this BC here. Now, we could if we wanted, it won't work, but we could if we wanted, try and load a 16-bit label value into our 8-bit accumulator here, and of course that will fail, but it won't fail in the point of view of crashing. Our assembler will tell us, hey, what you're doing there doesn't work. You've tried to load a value that is too high for that 8-bit register there. But if our I am a label started in the first 256 bytes of memory, it would work just fine. Now, we can use these symbols in pretty much any way, give or take, as I say, as long as we don't confuse the assemblers. Depending on your assembler, the level of the mathematics and things you can use might be an issue, but generally speaking, we can do anything we want with these that we would use a normal numeric value for. So subtract 8-bit, compare 8-bit, out to port 8-bit, or loading BC from memory address I am a symbol. All of these are perfectly fine, and we can even do mathematics. So we could do subtract 8-bit minus 1, or we could do subtract 8-bit minus I am a symbol, or whatever. We can do all kinds of things, and as I say, generally speaking, it will work fine up until the point where the assembler gets confused and our syntax becomes too complicated, or there's sometimes limitations in the mathematical abilities of the assembler. The WinApe one doesn't support multiplication and division first. It always works in the consecutive order, which can cause problems. So as I say, there are limitations, and again, you need to check your assembler documentation. But generally speaking, they're very powerful, and the big advantage with using symbols like this is we can, in the case of things like ports, we can define a symbol for our speaker port or something, and then use the name speaker port, so that later on when we're looking at our code, we don't need to remember what port BF was or something like that. We can just see, oh, speaker port, obviously that's a write to the speaker. It makes our code much clearer. That's why looking at assembly source like this is nice and easy. But if you disassemble code, because all of those labels and symbols are lost in the compiled code, that it's much harder, which is why I don't do it. But anyway, so that's how we can use labels and symbols. Now the next one we're going to look at is the org statement. Now this is very, very platform specific. There is actually a secret org statement in all of our code already. It's in the headers of the code I write, and this will define typically where our program starts. Now this is another one that depends heavily on your assembler. Now some assemblers will allow multiple org statements within the same file. Some will only allow one. Some assemblers will pad when they're given a second org statement so that there's enough space so that the next org statement is at the address specified. Others will just change the code and start compiling the labels to the new org statement. Now the org statement itself stands for origin, and what this tells you the assembler is, well, the next line of code that you compile after this command will be at memory address 4000, and this is used for things like a label that will now be given an address based on starting from 4000, and also it will, as I say, often be used by the assembler to pad the file. So if the memory address before that was much lower, lots of zeros will be put in place to pad it to this newly specified origin. So whatever our origin was before, it will now be 4000. Now another thing I do need to point out that I have come across with some assemblers, a VASM, can get confused by this. If you put certain kinds of command in before the origin statement, like a list statement for example, which is a compiler directive which doesn't compile to any bytecode as such, it can accidentally trick the assembler into thinking that that's the first command, and then it will put a huge amount of padding in when you maybe didn't want any. It does depend on your assembler how the origin statement works. Now, in the case of the VASM assembler, once we've specified the first origin, a second one will cause padding to occur until that second origin. Now, we've tested this here in a very simple way. What we've done is we've loaded BC with the address of the label before org, which is before our second org statement. As I say, the first org statement is in the header of our file, which will define the address that the program is loaded to in memory. If you want to see more details of that kind of thing, I've got a Hello World series which looks at a single assembly file. It's a very simple example for each platform, so please take a look at that if you want to see that kind of thing in detail. But as I say, once we've got our first org statement, the second one will cause padding. So we've loaded our before org address, we've then done an origin, and we've got 3 different origins here for 3 different systems, because it's going to depend on the position the code's loaded in to the memory. But then we're loading the after org label into our DE address here, and so we've got 2 register pairs here, one that's the address before the org statement and one that's the address after the org statement. and you can see BC had the address 61AA, so that is effectively the line of code that was this here. So that's that line of code there. And then our second one, DE, has been loaded with a memory address 9000, and that's because we've specified an origin of 9000 on the ZX Spectrum here, and the assembler has padded to that memory address as required. So that's the ZX Spectrum version. Well, let's try the Sega Master System. Okay, so here's our Sega Master System, nice fast startup for the Sega Master System. So again, we've loaded these, but this time our origin was 4000. So our original starting address was just 01AA, a very low address, and that's because the Master System has basically no firmware, so we're starting from memory address 0 with our program code. Whereas on the ZX Spectrum, our first origin statement will be memory address 6000, I think it is, and so we're padding away on from that. But as I say, on this system, we start from a very low memory address, but then our org statement was again 4000, so our code has been padded to that 4000 address here. Now, generally speaking, you're probably going to only want one origin statement at the early stages within your code, but it might become necessary as you're getting cleverer and becoming more advanced in your programming. There might be areas of memory that you want to reserve for certain purposes. For example, if your program's starting at memory address 0 and you want to allocate the 4000 to 6000 range for some screen memory or something like that, you might want to jump over that range with an origin statement or something like that. Or it might be useful if you're bank switching. I calculate the bank switching manually by myself. So if I've got a 128K program, then I will put origin statements in and padding, and so that I make all of the sections of the code into separate blocks, and then I page them in accordingly. It's not something you're going to need to worry about too much. At this stage, you'll probably just want one org statement at the start of your program, but as I say, it's a definition that you will definitely need to know about. Now, another one we're going to look at, which is a lot of fun and very useful if you can get the hang of it, is conditional compilation. Now, conditional compilation is something, again, that you won't need in the early days, but this is a very handy thing when you're trying to write advanced programs, when you're trying to write test versions of your programs, and when you're trying to work multiple programs. Maybe like in these cases, all of my programs run on multiple systems, and you may think, well, how does it do that? Well, what it is there's conditional compilation. There's blocks of code which only compile if a certain symbol is defined, and that symbol is usually build CPC, build MSX, something like that. And so this switches different parts of the program on and off, and the parts that are switched off simply don't exist in the resulting binary. The assembler just skips over that section and won't assemble them at all. So that's what this does. Now, what we're doing here is we're defining a symbol called positive, and we're just giving it a value of 1. Now, the value doesn't matter. It's just the fact that the symbol positive has been defined. And so what we're saying here is if defined, positive, if positive is defined, which it is by this line above, then we're going to compile these lines of code. Otherwise, we're going to compile these. That's what else means. Otherwise, compile these. And that's the end of this conditional block here. So basically, we are going to compile two possible versions of this program. One is going to say hello, and one's going to say goodbye. And the only line we'll change to switch between the two is this one here. So if we just compile this now, we get the very positive hello glorious world message. So that's very nice there. But if we're feeling very negative one day, well, we can just disable the positive here. We can just run this line out, compile again, and now it says goodbye cruel world. And all we've changed is one line of code, and it's this condition here that has done the job of switching the two over. And as I say, that's how my programs work on multiple systems. It's also how you can have different builds of your program. Maybe one's a debug build, which shows some values to the screen for testing, or maybe it's got extra code in that makes the game slower so you can see what's going on, things like that. You then disable your debug equals 1 statement at the top of your program, recompile, and you've got the fast version for release. Things like that. Or you may have, if you've got a Patreon site, you may want to have a free version for the public and a Patreon exclusive version with added features. Well, you can just have a command at the start, and you can build the two versions, one for your premium viewers and one for your free viewers. It's really handy to be able to do this kind of thing. There's so much flexibility, and as I say, unlike having branches within your code, this doesn't take any extra data space in the resulting file for the code that was not compiled. We could have done this with loading the accumulator with a variable and then doing a comparison, but that would have increased the length of our code. But with the if-def statement, only one of these two lines actually exists in the resulting binary. So it's much faster. It doesn't waste any speed, it doesn't waste any memory, and we don't have memory or speed to waste on a Z80 system. So conditional compilation of our code, very handy. I would totally recommend you take a look at it. Okay, now what we're going to look at next is, again, I think it's something we've seen in passing before, but we're going to be doing some definitions of data. So there's going to be a great many times we're going to want to have bytes of data within our code. These may be something as simple as a string of text like these. These are bytes of code here. They've got a 255 at the end as well. Or they may be number values, maybe an X and Y position, maybe a memory address, maybe a life, maybe the starting life for our player. Who knows? It could be anything. And that's what the point of this is. I'm showing you the things that you will need in your toolkit to use in your final programs. How you use them is entirely up to you. And if you don't know how you're going to use them yet, I'm sure you will start to figure it out as you start to think about what you need in your program. So here's some examples we've got. Now this first one is dB, which are defining bytes. So I've specified 2 bytes here. We could have just specified 1. We can specify a whole string separated by commas. The next one is define word. That's of course a 16-bit value on the Z80, so 2 bytes effectively. Now 0666 is a 16-bit value, but of course it will be stored in little endian in memory, but the assembler will work all that out for us. DS is defining a sequence. That's a sequence of bytes. Now if we just specify DS4, that's basically creating 4 0 values by default, but we can specify something else. So here we specified DS4 and the value 11 in hexadecimal, and that will pad out 4 bytes with 11. And then finally at the end here we've defined another word, a 16-bit value there, and again this is just as a test so we can see the end of the defined sequence, and we're going to show these to the screen. So let's fire this up. Let's take a look at what happens. Okay, so we got at the start here 6977 and then 6606, and these are these bytes here. 6977 was 2 bytes defined consecutively, and then 0666 here has become 6606 because, as I say, it's little endian. We then did a DS4 followed by a DS4, 11. The DS4 defined 4 0 bytes. That's just some space that we can maybe fill in later on with make our program use those bytes for something. And then we defined 4 bytes of 11 here. Now, why would we want to do that? Who knows? Maybe that's a bitmap pattern. Maybe that's our background color that we fill our screen with, something like that. Who knows? But as I say, if we want to define bytes of filled area that aren't 0, that's the command we would use on this assembler. It will differ possibly on your assembler. And then we're defining another word, FFEE, and that's just to show the end of this block of data, and you can see it here after the ones. Okay, so that's how we can define random bits of data, so to speak, anything we happen to fancy that particular day. Now, another command that is very useful when combined with this is the align command. Now, this command does vary on WinApe to VASM. On VASM, we specify a number of bits. So align 8 is basically saying align the next line of code so the bottom 8 bits are all 0. So basically what this is doing is making sure that the alphabet label will start on a memory address like 0100 or 0200 or 1000. The bottom byte is always going to have to be a 0 because we've aligned to an 8-bit boundary here. Now, why would we want to do this? Well, we'll see why in our code, but first of all, basically this alphabet is very simple. All we've done is we've started with an ASCII character A, and we've done all the way up to Z in a sequence here, so 26 bytes of ASCII characters, and they're aligned so that they will be on a boundary where the bottom byte of the address is 0. Now, what we're then doing here is we're loading HL with the address of this sequence, and then what we're doing is we're loading L with 0, and we're then going to load a letter from the address HL and show it to the screen. We're then going to load L with 1. We're going to load a letter from the resulting address. Remember, we've loaded HL originally with the alphabet address, and then we're changing the low byte. And remember, the low byte for the start of the alphabet sequence will be a 0 because of that align. So when we're repeatedly changing L and then loading in a letter and showing it, what's going to happen? Well, what we've effectively done here is we've created a lookup table which allows us to look up letters within the alphabet. So if we look up letter 0 and show it to the screen, and then show letter 1 to the screen, and then show letter 2 to the screen, we will show ABC here. And what we can do here is if we change this last one to 25 and we run again, well, now we've shown ABZ, because as I say, effectively we are now calculating via this lookup table and via loading the HL pair with the address of the lookup table and then changing the L byte of the pair accordingly and reading in a byte from that lookup table, which is a letter, and showing it. We've created a command that allows us to look up the letter within the alphabet. Now this is 0 based, so 0 is A. Well, if we wanted it to be based on a 1, maybe we want to think of A as the first, well, we could just put a dummy character in here. We'll just put a space in here. And then when we run this again, well, now letter 0 would be space. So let's change this to a 1 here and run again. Well, now you can see we've shown AAY because letter 1 is now A and letter 25 is now Y. Letter 26 would now be Z. So the important thing here is this lookup table has to match the way that we're using it. Another way we could have had the same effect is we could take away the 0 entry here, and if this was a subroutine we could have just done a dec L here to correct this to be a 0 based lookup when we looked up from A. Now I'm not really suggesting that you're going to want to convert numbers to alphabetical letters like this. You can do an ASCII subtraction instead. I'm showing you a way that you can create lookup tables, and this is a simple way that's very visually clear. Lookup tables can be essential for very fast code. Now I'm currently writing some code that horizontally flips sprites in the x-axis. Now that's something you're going to often want to do, but unfortunately because a byte of the screen memory contains multiple pixels, and because shifting the bits around that contain those colors can be difficult, the best thing to do is to create a 256 byte lookup table, pre-calculate all of the flipped equivalent pixels, and then use that lookup table during the sprite drawing routines in real time to flip the sprite and draw the equivalent flip sprite with not much loss of speed to the screen. So as I say, while this is a very simple example that you're possibly thinking, well, I can't see how to use that, as you start to do things in your program code and you start to do things that are very repetitive, transparency, sprite flipping, things like that, you might find that a lookup table is exactly what you need, and often you're going to want to align them for extra speed. Now we could have alternatively loaded the HL address of alphabet and then added as a 16-bit value the offset we wanted. Maybe we could have loaded B with 0 and C with the number and then added BC to HL. But this way of doing it is faster. And as I say, if you're working with sprites and you're plotting lots and lots of bytes to the screen every single frame, you want the speed and you sacrifice the memory, and that's often the trade-off you make when you start writing your advanced games and things. You have to choose. You can either sacrifice speed or you can sacrifice memory. That's often what it comes down to. Now that's one trick, and another trick we can do with these aligned tables is something known as vector tables, and this is a bit like writing our own commands. So what we're going to do here is we're going to create a vector table, and we're going to create a command called do command. So we're going to specify a numbered command in the accumulator here, so command 0, command 1 and command 2, and then we're going to run our do command. Now our do command, this one hasn't been aligned, so basically we're not specifying that it's going to start with the bottom byte of 0, but after this is now a lookup table which contains 2-byte one-word entries, and each of these is actually a label. So these are show cow, which will show the string cow, show says, which will say says, and so on. So we've got a whole sequence of addresses of subroutines that we might want to run. Now what do command is going to do is it's going to load B with 0, C with the command number. We're then going to load HL with the address of the start of this lookup table. A vector table is a lookup table of addresses basically. And then we're adding BC twice, and the reason we're adding BC twice is because we've loaded B with 0 and C with the value in the accumulator, and the accumulator is going to be a command number either 0, 1 or 2 in this example. So we're adding it twice because each entry in this table is 2 bytes, so to get entry 1 we need to add 2, and we're doing that by adding BC to HL twice. We're then loading the accumulator from HL, increasing HL, loading H with HL, and then loading L with the accumulator. Well, why are we doing that? Well, we want to get the HL pair from the memory address in HL, but if we loaded L first, then we would have ruined the pair that we're reading from. So we load into the accumulator as a temporary, we then load H, and we no longer need HL, and then we load L from the accumulator, which was that temporary L. We have to load L first because we're a little endian system, so the low byte comes first. So HL now contains one of the addresses in this lookup table. And what we then want to do is we want to call the subroutine that we specified by our command number, and we do that with this rather odd JP in HL in brackets command, and this means jump to the address in register pair HL. So that will now jump to the address that we loaded in from our vector table, and that will be the address of the command that we specified by the number that was in the accumulator. All very complicated, I know. Well, we're going to test this one, and we have to test it on the CPC. It won't work on some of the systems because the next example is going to do something even trickier. So let's fire up our CPC emulator here and let's see our command in action. Okay, a little bit slow there. So what did we do? Well, we loaded the accumulator with 0 and we ran the command do command, which will show the command 0. And then we did command 1 and then we did command 2. Now we've got these very simple commands here. There's a list of them here, and each one does exactly what it says. So command 0 will show the word cow, command 1 will show the word says, and command 3 will show the word moo. And so we've shown here cow says moo. So that's the result of our 3 numbered commands here. And so this do command function here is effectively a routine that will call a subroutine based on a number that we specify. Now this is quite handy because basically what we've now got is we've got a series of subroutines that we can call based on a byte, and we can write that byte in from somewhere else. You know, we could make the different directions of our joystick and run different commands. And what I often do is I will create a sequence of bytes within my level code, which is a bit like a virtual machine, and these will be passed to commands like this that will actually look those bytes up in vector tables and run subroutines based on those bytes that were read in from the sequence of code that make up the level data. Now, this here is basically not really any more efficient than just calling the cow says moo examples directly. But as I say, we could load these accumulator values from our joystick or from some other external source or our disk or something, which would make the code run differently each time. But the other thing we can do on the Amstrad CPC is we can actually create our own special command. Now, a call is 3 bytes, but there's a way we can make a 2-byte call using an RST. Now an RST is a reset, and these call to low memory addresses, and RST0 is reset 0, and that calls memory address quadruple 0. This will only work on the CPC because on the Spectrum that's a read-only address, and so calling this will actually reset the Spectrum. But on the CPC that address is memory, so what we're doing here is we're copying the command RST test to memory address 0. We've got an LDIR which is going to copy RST test. What does RST test do? Well, it's a little bit complex, but what it basically does is it swaps the memory address at the top of the stack, which is the return address of the calling command. An RST is actually a call. It's a 1-byte call command. It's a very short call command. So it pushes the return address onto the stack. So we're now swapping the HL and that return address. So the HL is now the return address. We're then reading a byte from what was going to be the return address, increasing the return address and swapping it back onto the stack. Now HL has not been altered during this because we swapped HL with the value at the top of the stack, so HL was now at the top of the stack, and we've got the return address in HL. We read in from the return address, incremented the return address, and then swapped the return address back onto the stack and the original HL out of the stack. So HL hasn't changed, the return address has gone up by 1, and we've got 1 byte from that original return address. And then what we're doing is we're jumping to do command. Now do command, of course, is our test command that we were using before. Now what we've effectively done here now is we've now made our own special command via RST. Now RST0, despite the space there, RST0 is a single byte command, and then after that we've defined a byte. And because of this program here, what this will do is it will be the equivalent of loading A with 0 and calling do command. But whereas this, the call do command would be 3 bytes and the load A 0 would be an extra 2. So that would load A, 0 call do command would be 5 bytes. That is just 2. It's less than the call by itself. So that is a very, very small way of calling a subroutine. As I say, the call alone would have been 3 bytes. And so we've now almost created our own command called do command basically, and we can now run the subroutines within our vector table via a single byte number. Now, some operating systems do this by themselves. The Enterprise has an OS call that is an RST, and the assemblers actually convert that to look like a command in its own right. As I say, the Master System doesn't have an operating system, but virtually every system with an operating system will have some default RSTs that do system calls of some kind, and maybe you call them in this way, or maybe you load the accumulator before the RST. But as I say, they will often use an RST, and the reason they use an RST rather than a call is an RST, the RST 0 to RST 7 are a 1 byte command, whereas a call would be a 3 byte command. So these are a way, if you are very short of memory and you need to do a command an awful lot, these, as I say, are 1 byte shorter than the equivalent calls. So a tricky way of doing things. And what we've done here is, before we did command 0 followed by command 1 followed by command 2, this time we've done command 0 followed by command 1 followed by command 3. Command 3 is show woof. So we've made the rather dubious statement, cow says woof. Well, our code is very logical and has worked correctly, but maybe we've got something wrong upstairs, because I'm pretty sure cows don't say woof. But anyway, nice amusing little example there. Of course, if we wanted to be pedantic, we could create a function called dog, and we could say dogs say woof as well. But I don't think we really need to go that far. I will leave that for you to do in your own time. Now, the last one we're going to look at today is macros. Now, macros are similar to conditional compilation in a way, but what these are is where we can define a string, and the assembler will replace every iteration of that string with the contents of a macro. So here we're defining a macro called showString, and it has a parameter, and the parameter we're calling myString. Now, the operations that this macro will perform is to load HL with the address of myString. Now, that slash there that's specific to this assembler. VASM, you put a slash there to specify that that's one of your parameters, myString in this case. Some would use numeric parameters, it just depends on the assembler. So here we're loading HL with the address specified by the parameter. We're then calling printString, we're then calling new line, and that's the end of our macro. Now, here we've got the macro showString, and we're specifying the hello message, and then we've got the macro showString, and we're specifying the goodbye message. Now, hello message and goodbye message are strings within our code. We saw them before for that hello glorious world and goodbye cruel world, and we're going to see those once again right now. So here's our program, and we've shown the two strings to the screen. Now, hello glorious world and goodbye cruel world. Now, we could, of course, create a subroutine called showString, and we could have called that subroutine, and we could have loaded HL with these values, or we could have even been super clever, and we could have loaded it from the bytes following the return address in the same way as we did here. I could have loaded that in. But there's a big advantage to macros. Now, as I say, this isn't a call, this isn't a subroutine, this is a text replacement. So this one line of code here is replaced by the assembler with these 3 lines here. So this is 3 lines, this first showString line here, and this is a separate 3 lines here. So this is all separate code when it's compiled. It's not a subroutine. Now, this allows us to do more clever things, more complex things than we could maybe have done with a subroutine. It's also, of course, faster. Calling subroutines involves return addresses and things like that. And again, as I said before, we're often making a choice between having speed and having memory. We can have performance, but we have to eat up our code space, or we can have very small code, but we lose the performance. Now, the RST command here that we basically wrote our own command that was 1 byte shorter than call is slow, but it saves memory. Using a macro to do what we could have done with a subroutine is fast because there's no calls, there's no returns, but it's going to eat up our memory. And as I say, macros are fantastic for making lots of different versions of a command that are only very slightly different. Like in this case, the only thing that's different is the address loaded into HL. They also are very handy if we want to create huge blocks of code, which is known as unwrapped code, unwrapped loops. Maybe you want to do 1,000 pixel plots. Well, you could have a loop that loops 1,000 times, but you lose a little bit of speed every time you do that loop. So maybe you make a macro that does the pixel plot 10 times, and you use that macro 10 times in a row. A huge block of code, but extremely fast. As I say, these are the trade-offs you end up making. So macros, again, another thing that you don't want to worry about in the early days. It's a thing to bear in mind in the back of your memory, because there's going to come a day where you want to do something very clever, or you want to do lots of very slightly different versions of the same piece of code in lots of different places, and a macro will be the thing that will do that for you. But if you're not using VASM, or you want to do something that's more complex than the very simple example I've shown here, you want to check your documentation, because the syntax with regards to labels that are part of the macro and the syntax relating to parameters does vary depending on your assembler. So please check that out. So there we go. That's all we're going to be covering today. If you've liked what you've seen, please like and subscribe. I do have a lot of other tutorials apart from this basic Z80 series. I've got the multi-platform series where I do go into more stuff like what you've seen today, which is where we're not so much discussing the commands themselves, but discussing a wide variety of ways that you can use those commands that are independent of any specific system, but ways that you can build those commands into structures and tools that you can use in your own programs. As I say, things like vector tables, lookup tables, these are tricks that you can do with the commands. They're not commands in their own right, but they are absolutely essential to writing good and complex code, because as I say, if you're going to create the fastest demo or the fastest game, you're going to have to employ a lot of tricks in the process. Anyway, hope you've enjoyed this today. Thanks for watching, and goodbye.